Hello, everyone, and welcome back. I hope that everyone's uh, midterms went well. Um, I was really happy with how you guys did on the our midterm, and you'll get to see those in the coming weeks. You'll get to see the midterm. We'll look at that a little bit. So for today, sorry I can't be there, but I'm going to introduce to you the next topic in the unit that we started before midterms, which is on volume. So first, you've dealt with volume and geometry, and in here, or I should say, one of the figures that you did examine the volume for was a cylinder. So I've drawn a cylinder on the screen there, and the only thing perhaps is that that cylinder is laying on its side, but the cylinder, right, it has right over here we see it has the base radius r. It has a height of h, and so the volume that we have for that cylinder is pi r squared h. And this here is a formula you're going to kind of see used in this unit on volume, but it really is, not too terrible to think about how we arrive at that volume formula, because the basic idea is that um, area of a circle we know is simply just this pi r squared. And to find the volume of this cylinder, the idea is we want to try and find all the space in here. Well, we just take the area of one circle and then we just kind of like add up all the circles that are happening from left to right, which is captured by that h. And thus, pi r squared, we multiply by h. And that's going to be consistent with what you're going to see in this unit. Like that's how we're going to sort of find the volumes of these solids by sort of looking at the cross sections and trying to determine like, well, what's the area of those cross sections, and then sum them up. So what are the solids going to be that you're going to find the volume to in this unit? Well, um, the way that the solids are going to be formed is by starting with a region, R. That'll be bounded by, in this case, it's bounded by this f of x graph and the x-axis. But there'll be a region bound in the xy coordinate plane, and what we do is we revolve that region about a line. It could be the x-axis, could be the y-axis, and so on. And when we revolve that region, then a solid is going to form. Now, I do apologize that I'm not there because I usually have a visual to show you sort of a solid being formed by revolving a region similar to like this here. But um, if you take a look at two things, so here, if this will allow me, or maybe it won't, not here. I guess that one site's not going to allow me. So here um, we have a region. This graph here looks almost like perhaps like the square root of x graph. And if you think about that graph and then down to the x-axis, this forms a region here. And again, we can start just rotating that graph, in this case about the x-axis. And you might not be able to really see perhaps any solid right now, but um, again, that revolving is going to form a solid. Revolving that region will form a solid, and there in particular is the solid. And if I perhaps rotate that region, you could perhaps get a better sense of that particular solid. Now, the one thing I'll say is that in all these problems you're going to find the volume to, you're never really going to have to know exactly what does the actual solid look like. The key thing will always be identifying what are the cross-section shapes. And hopefully you would agree that when we revolve that region about the x-axis, wherever we look at this solid from left to right, from the side over here all the way over to the right, all the cross-section shapes are circular in nature. And so what we're going to do is, in a moment, we're going to develop a formula to get the volume of this solid or any of these solids formed by revolving regions about a line. Is we're going to examine cross sections, identify the shapes, which in this case all these cross section shapes are circular in nature, and then we're going to go from there to find the volume. Now, the last thing I'll perhaps say about, stop this rotating, say about this particular solid here is that while if we slice cross sections from left to right, they are all circular in nature, but technically, no matter how fine-tuned we slice the regions, they're going to have some uh, width to it. So, in a way, technically, um, cross sections are going to be cylindrical in nature because they'll be circular, yes, but each one will have some sort of width. So, with that being said, here is just a kind of the picture of that solid formed. And to develop the formula, what we're going to do first here is, here is that graph that I showed you being revolved about the x-axis. And what I've drawn here are technically 6 of these like cylindrical disc cross sections. And so what we'll start off doing first is we'll identify, based upon this graph, whose function is just given by f of x, we'll determine, well, what is the volume of just this first cylinder? And then from there, you'll see we'll then go from one cylinder to the 6 cylinders here. And then from there, we'll proceed to how do we find the volume of the entire solid? So with that being said, again, first we'll look at this cylinder here that I've highlighted in yellow and I've labeled as A. And so, all right, for the volume of that cylindrical disc, again, volume of a cylinder, pi r squared h, so we need to know the radius of the base cross sections, those circular base cross sections, and then the height. So, for this A cylinder, the radius, hopefully you would agree that the radius is going to be of that cylinder there is going to be that length, which because of the graph of fx, that length is going to be equivalent to f of the x value right here. So that r, or I'll label that as r, that r we can say is just equal to f of x. And then for the height of the cylinder here, well, that's going to be that sort of width there. And for now, hopefully you would be okay with just labeling that as some delta x. It's going to be some width. It's going to be, hopefully somewhat small, but we'll just label the height there as delta x. So the volume of that cylinder A would be equal to just pi times the radius, which we're labeling as f of x, whole thing squared, times the height of delta x. Right, and we have the volume of that just one cylindrical disc cross section. Now, from here, we want to try to do the same for all of the 6 cylindrical disc cross sections that we have here. And the idea is that each of the other cylinders can be found, the volume can be found in a similar way. The radius would be some f of x value, depending upon where the cylinder is located, and the width would be some delta x. So since essentially all of the other cylinders would have the same format of the volume, to help ourselves with that, we can say that, yeah, it should still be similar to the volume of our cylinder A. It should be pi times some f of x, but I'm going to label that as f of x sub I because we have 6 different cylinders and the x values will be at different locations. But that f of x sub I should still be squared. The delta x, we could try to cut up all the cross sections of equal width, so the delta x perhaps would be the same. And now to sum up all the 6 cylindrical, the old cylindrical disc, instead of writing it out 6 times, we could just write sigma notation and say that I is going to range from not 1 to n, but 1 to 6. And voila, like that, we have the volume for those 6 cylindrical disc cross sections. Now, we're developing things, and ultimately we want to find the volume of the exact solid, which is this here. And the problem with just the volume of the 6 cylinders that we have established the formula for with that notation there is that it's not going to be 100% accurate. Right? We can see here that obviously these cylinders, technically, they would perhaps be an over approximation for the actual volume. So to get the exact volume of this particular solid, what we're going to have to do is we're going to have to increase the number of these cylindrical disc cross sections and continue to increase them. And guess what? Guess where we're gonna increase them to? Well, we're gonna increase them to and send them off to infinity. And when we do that, the delta x will become infinitesimally small because the number of these cylinders will go up to infinity. But that's the basic idea of how we get the exact volume of this solid that we have here. So the exact volume of that solid with cylindrical disc cross sections, right? It's going to be, I'll take that sum from I equals 1 to some n, and it is pi times f of x sub I, whole thing squared, times delta x. And again, this would be the volume of n cylindrical disc cross sections, but we have to send that off to infinity. And what notation have we used this here to help send something especially off to infinity? Well, that's going to be the limit as n races off to infinity. And that technically right there represents the exact volume of this solid form by revolving the region about the x-axis. But we typically don't work with this notation here when we go to find our volumes of these types of solids. Instead, if you recall, the limit of a sum, that turns into a definite integral, and limits of integration I'll just write from x equals a to x equals to b, and the integrand becomes the pi f of x, that whole thing squared, and then the delta x, well, that becomes the dx that we should see at the end of each one of our integrals. And so the volume for any one of these types of solids that, when we look at the cross sections, have these circular, cylindrical disc cross sections. This is the basic formula. And the one thing I'll highlight here is that the integrand, if you notice it, it's pi times f of x squared, where, again, remember, f of x is essentially the radius of each respective cylinder. So pi times the radius squared, hopefully you recognize that as really just being the area of our circle, just like we had over here. So any one of these types of solids, this is our volume formula, and the integrand is going to be, and I'll always reference this, it's going to be our cross-section area. Any volume problem that we deal with in this unit, it's going to be a definite integral, and the integrand will always represent the cross-section area to our solid. So that being said, we'll look at a couple examples. So the first example here, we're going to set up an integral that represents the volume of the solid form when the given region is revolved about the given line. In this first problem, we're going to revolve about the x-axis, and the region here is bounded by y equals square root of x equals to 1, x equals to 4, and the x-axis. So again, we're going to revolve that region about the x-axis to form our solid. Now, the volume of that solid, well, we just started off. And again, we're revolving the region about the x-axis. Hopefully we agree that the cross-section shape is going to be circular. And I'm going to just highlight and write disc cross-section. Because for now, again, we just started with volumes. There are going to be other types of solids that had different cross-sections. And so I'm just going to highlight here, we have a full-on disc cross-section for each of the cross-sections of our solid. So because of that, again, our volume formula is this here. It's pi times the radius squared. So the radius of our particular circle, hopefully you would agree, the radius, if you look at any type of cross-section here, if I just look at perhaps this cross-section right here, that would be formed by revolving the region about the x-axis, the radius of that particular cross-section is going to be given by the function whose equation here is square root of x. So I'll write r equals to the square root of x. That's our radius. And so now for the volume to our solid, it's a definite integral. The integrand is pi times our radius, which is the square root of x, whole thing squared, dx. And now for our limits of integration, these two values here, x equals a, x equals to b, just like when we dealt with other integrals and especially area, X equals A is going to be the left-handmost portion of the region, and X equals B would be the right-handmost portion on the region. So in this case, those X values are 1 and 4 respectively. And so I'll just write 1 and 4 there. And voila, like that, we have the definite integral that represents the volume of the solid form when that region is revolved about the x-axis. All right, so if we look at this next problem here, again, we have a region that is bounded by the graphs of y equals e to the x, y equals to 0, x equals 0, and x equals to 5. So we can kind of see those particular graphs here, and we're going to revolve this about the x-axis. So, some people, to help visualize things, they may, for themselves, just draw like one cross-section in the region, and perhaps then just say, oh, I'm going to draw my circular disc cross-section there. Again, some people that helps see and visualize things, but just like the last problem, here we have a full-on disc cross-section. The radius of this disc cross-section, hopefully we agree, is that length there, which that length can be captured by the graph of y equals e to the x. So I'm just going to now write that our radius here is e to the x. And now, because we know there's a disc cross-section whose radii are essentially just e to the x, the volume to this solid will be pi times our radius, which is e to the x, whole thing squared dx. And our limits of integration would go from the left side, which is at x equals 0, to the right side, which is x equals to 5. And so we'll just put 0 to 5. And again, voila, once again, like that, we have the volume of this solid formed when it revolves about the x-axis. All right, so we'll look at one last problem here. So here, the region that is going to be revolved to form our solid comprises of y equals square root of x, y equals to 3, and the x-axis. So the region, right, is that yellow region, and we're going to form the solid by revolving this, but we're going to revolve about the y-axis now, not the x-axis. So this region, right, is going to get revolved that way. And you don't have to do it, but I'm just going to help visualize things perhaps a little bit. I'm going to draw a cross section. The cross sections, and what's going to be different here is that the cross sections are going to be horizontal. So like here perhaps is one of those cross sections. And what's going to happen here, there's still going to be, in terms of cross sections, they are all going to still be circular and disc cross sections. But now the problem is going to be that they are all horizontal. In the example number 2, and even the problem before that, the cross sections in each one of these other cases were vertical, and we found the respective radii. The respective radii were in terms of x. But now, if you recall back to when we looked at area of regions, and I know this wasn't something that some people so much like, but when you want to measure out from the y-axis to some point, well, in these cases, you have to switch everything over in terms of y, meaning this y equals square root of x, we're going to want to solve for it in terms of y, and our integral here has to be in terms of y. There's no two ways about it. Unfortunately, in these cases, you do have to have everything switched over in terms of y. So, with that being said, y equals the square root of x. If we solve for x, hopefully we agree that would be x equals to y squared. And this measurement here, right, going out from the y-axis to our graph, it's going to this graph, that is y equals the square root of x. But since we're going out horizontally, the measurement here would not be square root of x. It has to be in terms of y. It would be y squared. So the radius of each one of our circular cross sections here, our disc circular cross sections, is r equals y squared. And for our volume, the volume would be a definite integral of pi times our radius, which is y squared, dy. And then for our limits of integration, They also have to be in terms of y. So the lowest y value in a region, the lowest cross section would be at y equals to 0. And as our cross sections go from there all the way up to the top, the highest cross section will be found there at y equals to 3. So our limits of integration here would be from 0 to 3, and there would be our definite integral capturing the volume of this solid that is revolved around the y-axis and has circular disk cross sections. I hope this video helped you out with understanding an introduction to volumes of solids. I'm going to post a worksheet, some problems to try and practice, and I will also potentially, I don't know exactly when, but I'll try to post solutions to that as well. So if you have any questions, need any help, you can try to message me on Google Classroom, and I'll try to get back to you as soon as possible. Thank you for watching my video, and I hope everyone has a wonderful day. Take care, everyone.